Okay, what we have seen all along the first hour is that if the force is a central force, the angular momentum is a constant. Angular momentum does not vary in time. So what does this mean? Its magnitude should not change in time. Whatever the magnitude of the angular momentum of an object is, it is the same now and same in 30 minutes from now and 1 hour from now. So it doesn't change in time. How about its direction? Should its direction change? Consider the Earth-Sun system. Sun is here, Earth is in motion around an almost circular orbit. The only way its direction would change is if or whether the position vector change, which doesn't change because there's the gravitational attraction. The position vector changes because Earth is in motion around the Sun, but its magnitude is not changing if it's perfect circle. How about the speed? Does the speed of Earth change in its orbit around the Sun? If you consider it's a perfect circle, of course. If it's elliptical, there are slight variations. So if it's a perfect circle, it wouldn't change. So the only way you would change the angular momentum magnitude is by changing the magnitude of the position vector, the distance to the rotation axis, or the momentum. Also the mass, of course, if the mass of Earth is just getting less or getting more by getting more matter from outside. We know that none of these happen, and Earth is almost on a circular orbit, not exactly, but almost. Therefore, and the force between the central object, the Sun, and Earth is a gravitational force, and there is a central force. Therefore, angular momentum should be conserved. Angular momentum is in the direction that is perpendicular to the position vector and the velocity vector. So if we take xy plane here, the angular momentum is always perpendicular to the plane in which the position vector and the velocity vector are both found. So the angular momentum vector should also not change. Not only its magnitude, and also its direction should be conserved. If the force is a central force, that means not only the magnitude but also the direction of angular momentum should be conserved. It should not change. So what does this imply? If an object is moving under a central force, its orbit of motion should be the same because the force is central, the angular momentum is conserved, it's not changing, not only the magnitude, and also its direction. So it should remain on the plane on which it's rotating all along. It shouldn't move in and out of this orbital plane. Would you agree with this one? One example is our home planet that is in orbit around the sun under a force that is the central gravitational force. Therefore, the angular momentum of Earth is conserved. Not only the magnitude that we estimated in the first hour, and also its direction. As a result, the orbital plane on which Earth is in motion should be the plane that it's always in. It doesn't move away from that orbit or orbital plane. But this is not the case only for the Earth. Any planet in our solar system, there are 8 planets. 8 planets in our solar system lie in the almost same plane. Their orbital planes are almost in the same plane. Their orbits are all in the almost same plane. I say repeatedly almost because there are slight variations, but they are so small that from a broader view you can say that they are in the same plane. So this shouldn't be the case for Earth only. It should be a global solar system-wide property. And the reason is simple. They all experience the same central force, which is the gravitational force between the planet and the sun. They all rotate under this central force. Therefore, they should obey the same set of rules. One is valid, should also be something valid for one, should also be valid in some similar manner for the other one. So we can conclude that a planet in our solar system or in a different stellar planetary system interacts with the sun, in this case our solar system, through the gravitational force, which is a central force. Therefore, the angular momentum of that planet should be conserved. Now, we have no doubt about it because the force is a central force. But more importantly, its orbit around the sun must always remain in the same plane. Earth's rotation orbit is in a plane that is always the same plane. This year, next year around, when the Earth goes around and comes back to the same point, almost. So broad view is telling us that it's almost the same plane that this should take place if the force is central, if the orbit is a perfect circle. But we know that there are certain assumptions that we are making to make such a statement here. Okay, now let's get into angular momentum business a little closely. Let's put the coordinate axis, say x and y, and an object here with a position vector r, there's a displacement in its position. Let's call that displacement d sub r. A small incremental change in its position, say in such direction. Therefore, the terminal direction here, when you add these two vectors, is the position vector original and after small incremental change, dr plus dr. So it's again another vector. Now we can express the angular momentum if we know the mass of this object, but we are going to express the magnitude of the angular momentum in a special direction, which is the direction that is perpendicular to the displacement vector. Let's call this, it's a little hard to see, so I'll make here. So this vector here is the component of the displacement, incremental displacement, that is perpendicular to the final r plus dr. So the magnitude of the angular momentum is going to be equal to m, mass of the object that is in rotation with respect to this axis at the origin, times the perpendicular component of the momentum. Now, what does this mean? If we write this explicitly, it's, I'm sorry, here, please correct this. This is the magnitude of the displacement vector. We know that L is r cross p. If we take only the perpendicular component, then the sine of the angle between them, which is 90 degrees, is going to be 1. It will simply be the position vector times the momentum component that is perpendicular to the position vector. So here I'm skipping a few lines, but please note that how we obtain this is through the same r cross p. But in the perpendicular component, we know that r and p are perpendicular, only the perpendicular component, so we simply write r dot p. R is the magnitude of the position vector, and p is the mass of the object times the velocity, but not just the velocity, but its perpendicular component, perpendicular to the position vector. Now, let's get back to this shape a little closer. Now the incremental change in distance, position vector, is dr, makes an angle here, theta, we can call, but instead let's call it d theta, a small incremental change in the angle as a result of incremental change in position vector. Now we will use this to write the perpendicular component of the velocity, because we know that the position vector r is whatever r vector's magnitude is. Whatever mass is given, it's the mass. Only sort of unknown or little hard to digest parameter here is the perpendicular component of the velocity. So let's look at it a little closer. V perpendicular is simply the rate of change of perpendicular component of the distance right here with time. This is dr perpendicular, that is perpendicular right there, and its change over time will give you the perpendicular component of the velocity. And this can also be written as r d theta over dt, because dr perpendicular is simply the position vector, the magnitude here, r times the angle. You know this very well from your high school curriculum. Angle times the radius will give you the circumference. Of course, this is a small segment. The angle 2 pi times the radius r will give you the whole circumference of a circle. If you have, say, 60 degrees, which is pi over 3, times the radius will give you 1/6 of the circumference. So writing it in this fashion is something you are very familiar, but you may not remember right away. If you don't remember, you should check those geometry notes. So now we expressed the perpendicular component of the velocity in terms of angular change. How fast this angle is changing is actually telling you the speed in the perpendicular component. So now we have the velocity or its perpendicular component, perpendicular to the position vector, in terms of r, that is the magnitude of the position vector, and the rate of change of angle. As this object moves or rotates, it sweeps an angle, area, and you can express that in terms of angular change. Its angle with respect to the origin is changing. It was here originally, now it came to this point. So its angular position changed. It was right here, now it's there. D theta away from its original angular position. Therefore, we can write the angular, let's rewrite V perpendicular is r d theta over dt. Therefore, angular momentum, or the magnitude of the angular momentum, is rm times v perpendicular, or m r square d theta over dt. So we can determine the angular momentum in terms of the angular change. So what is the assumption we made here? Did we make any assumption? No, we didn't make any assumption. But what we started with is the fact that if the force under which this object is rotating about a fixed axis has to be a central force. If so, the angular momentum is conserved. Now, what you see here is some extension that we can easily make without requiring any assumptions. Now, we will look at the same picture here is x, here is y, and here is the position vector r, and here is the displacement of it, dr, and the overall displacement is right there. So let's bring some color in our life. Here is r plus dr. Now remember, we have analyzed the perpendicular component and called this vector right here dr perpendicular. The component of the positional change that is perpendicular to the resulting position vector. Now, let's approach this problem from a very different view. Can we determine the area of this triangle, which is formed by the axis of rotation or the origin, the position vector, original position vector, and this point right here. So we are going to try to determine the area of this triangle. So what is the area? Let's call it area of this triangle. What is the area of a triangle? Biraz çalkalayın şöyle kafaları. So the area of a triangle is a one piece. If it's a right triangle, just like here, the multiplication of the length of sides which are perpendicular to each other divided by 2. So it is the position vector, original position vector r, times dr perpendicular divided by 2. Now, instead of the area, let's consider for a second the rate of change of this area. In other words, as this object right here moves, how would the area of the triangle that is formed by the position vector, the perpendicular component of the displacement, and the origin? So what is dA over dt is our question. So let's take the derivative of this one. Our original position does not change. It was there originally. 1 over 2 is a constant. So we have 1 over 2 r, which are constants, times dr perpendicular over dt. These are changing. This is changing. The perpendicular component of the position or displacement is a changing quantity. It was here at this given time, but in a few minutes later it will come here. So the position vector or displacement's perpendicular component is going to change. Therefore, we can determine the change in the area very easily. There's no doubt about it. So, what does this give us? We know that r perpendicular or dr perpendicular is, again, r times d theta remember once again, therefore we can write dA over dt, the rate of change of this area of the triangle here is 1 over 2 times r right here, and we will need to substitute r perpendicular or dr perpendicular with r times d theta. That will make it r square d theta over dt. So, yet we have another relation which wasn't related to what we are doing today, but somehow we recovered some terms that is very similar to our angular momentum expression. If we somehow keep these two in the same view, which is not seemingly possible, we can look at here, L is m r square d theta over dt, while dA over dt is 1 over 2 r square d theta over dt. So both have r square d theta over dt. If I multiply this by mass and multiply it by 2, I will get the angular momentum. So the angular momentum, comparing the two relations, let's call it S star and 2 stars, where 2 stars here and S star is there, you can express that angular momentum is twice m dA over dt. Now what is this? We need to interpret this final box. What does this tell us? Any guesses? This is not trivial, it's not right, something you can easily spot, but it's not very difficult either. What is this, first of all? A moving object which is moving on an orbit And we have seen that if the force is central, then this object will move in an orbit always in the same plane. So the angular momentum was conserved. Now, here there's no circular motion. We have just analyzed the component that is perpendicular to the position vector. To make our argument simpler, we could just drop those vector products. In the end, what we have seen, in the plane that the object is moving, it's sweeping an area. And that somehow is related to the angular momentum. If angular momentum is constant, L is not changing, the area or the rate of change of area should also be constant. It shouldn't change in time. So the object should sweep equal amount of area in unit period of time. So let's conclude that. Let's rewrite once again. Angular momentum is twice m. These are constants. Let's assume that mass is not changing. dA over dt, once again. When L is constant, namely angular momentum is conserved, then dA over dt is also constant. So what is the implication? Now the planet or the object is moving under this force, and its position vector is sweeping an area whose area will change in time, but not randomly. It will be constant in time. The rate at which the moving object sweeps area. It's going to sweep more and more area, but the rate of it is going to be constant. It's not going to sweep more area at certain times and less area at some other times. It will sweep the same amount of area in the same amount of time. This is extremely important for us as our home planet is going around the sun. It sweeps an orbital area. Well, we don't see that region, but it's moving on a almost circular orbit, which is not circular, which is elliptical. But still, it sweeps the same amount of area in the same time interval. Say, take 1 month, consider the sun, Earth 1 month ago, and Earth today, and determine the area on the plane over which Earth swept in 1 month. Do this experiment in 6 months, say when it's winter, start from the, say in June, in December, and then count for a month and determine the area that the Earth swept in its orbit around the Sun. Although the orbit is elliptical, you will find that it sweeps the same amount of area. Now, does this remind you something important from your high school physics or any course? You must have seen this somewhere. What does this remind you? Or does it remind you anything? It's a law which we are going to study next time. There are certain laws. I hear something correct. It's the Kepler's third law, or I'm sorry, the second law. We will study the 3 laws of Kepler, one of which is right here. A planet moving under a central force is going to sweep an area in its orbit, which will be the same area in the same period of time. That means the rate at which it sweeps is going to stay constant. Why? Why does it have to stay constant? Because angular momentum is conserved. And we expressed angular momentum in terms of area swept. And that's what we are going to study as Kepler's second law next time. Any questions? Now, at the very end of this section, there's a nice bit of reading that you can easily read in 5 minutes, known as Noether's theorem. It's not extremely difficult, but to understand it fully, it's not that easy. So if you are interested, you can do further reading on it. But what it states simply is that if there are symmetries in the way that a motion is governed, then there has to be some corresponding conservation laws. Remember, what we started today is a force that is a central force, spherically symmetric, and we ended up with the conservation of angular momentum. This is not the only case where we have conservation laws. Take the first law of Newton. Under an inertial system, in a frame, in a system in which there is no net force, you have momentum conservation. So the theorem here states that if there is symmetries, some symmetries, there is expected some corresponding conservation laws. But here we are going to only cover the angular momentum, and under certain cases, that is when the force that makes the object rotate is central, the angular momentum has to be conserved. Okay, so see you on Wednesday.